Make it athletic where Jim Schwartz.
Yeah, the Browns.
Wait, is his name Jim Short or Jim Schwartz? Schwartz. Maybe I'll tell you. You guys are like doing good. Have you guys worn my clothes before? I know. I have one. So that's good. I have some athletic. It's like a look here. Yeah, like it's mine. All in my like they're nice, but.
It works. I've used it. I have it.
Blue like sucks because it some of the stuff is really good and it's you're signing your life away.
Both of the lanyards, they're ripped.
Really?
Yeah, like one of them is all, one of them's thinner and has a hole in it already and getting bigger. And the other one, the like inseam is coming out and it was like.
No, that's yeah, like that's ridiculous. That's not ridiculous. Oh no, we have to. Yeah, I don't know. It's always funny talking about certain things with my guys because I just don't understand how much money it is when it depends on stuff. Like leggings, like some like most people, what people wear, they're $100. That's crazy. Yeah.
But the chair has to.
Anyway, some people did really good on this homework, but I just finished grading it like yesterday, but
That was a hard one.
well, it took a lot. It was hard to grade, like if you guys get them perfect every time, it's really easy to grade, but when it's like, all right, there were like two or three groups that got like over 100 in this. And then it was like, everyone else was like 65, or a couple 50s, so it basically like 50. If you got everything wrong, you got a 50, so 50 was like sinking ship. Anyway, so this thing, yeah, it's kind of like thermo stuff, I guess. Ambient. So I was asking you to say like, assume the highest possible temperature. So I meant the boiling point, like whatever the stuff boiled. Like in other words, the water's going to boil. That would be the highest you could get. Does that make sense? Or the three groups that made sense. Everyone else it didn't make any sense at all. So then you need to know like the altitude to figure out what the boiling point is. But when it's 2,000 meters or whatever, I guess it doesn't matter that much. It's only 1 degree different. And then you need to use the efficiency thing for. I'm just saying like the kind of the generic. Is like T hot minus T cold over T hot, or it can be like 1 over T cold over T hot, right? So everyone puts in like in centigrade, so it's not going to work. Like centigrade won't work here. That was the common mistake everyone made. Then if you put in centigrade, you get like 87% efficiency, and the actual number is like 22, something like 22. So any thermal equation, just use Kelvin straight off. I mean, some part of this, like the differential, you could use centigrade, but this thing will kill you because you divide by, like, say it was below 0, you'd get a negative efficiency, for instance. So that's not possible. So I don't know, maybe you can use just any thermal thing, just convert to whatever, to Kelvin. That was the main thing people did wrong, or they just didn't have any idea. But I think everyone got the Carnot efficiency. Like you kind of Google that, and then their efficiency was 0.12 0.2 or something, and the thing you get from Carnot is 0.22, so like 50% Carnot, which is pretty good, I thought. I mean, it almost makes you think that their numbers aren't right, that you couldn't actually reach that kind of efficiency with the kind of rig they have. Then here, I mean, if you had done this one right, and if you had realized that it was a boiling point, then you realize, like, if you wanted to go to a higher temperature, you'd have to either pressurize it, or you'd have to like use a heat transfer fluid, so you're not using water for it. So I think one group did that, said that, and everyone else kind of danced around it. I mean, some of them were better dancing than others, you know. It didn't really matter that much, but basically, anyway, and then so why do you get so it's like you did distillation columns, right, in thermo, and then you did multiple stage distillation columns. So why did you do that? Why don't you just use like one, just a pot boiling the stuff? So no one could really answer that. One group kind of answered it. So anyway, that's something that you should have gotten there. I mean, you should know like why it is that you go into there's two questions on here that are generic. Like, why do you go to multi-stage, and why do you scale up? Like, why is it that you scale up? So I think everyone should, that's probably important to know, like why you're doing stuff. I guess, I mean, it's good to be able to do the math, but basically to know why you're doing it. Anyway, the reason the multi-stage goes closer to equilibrium. That's the kind of the answer for this. But one group kind of said that. And that there's like magic word answers to these. You know, like it's almost like ChatGPT should be able to answer this. I tried, but I did put this into ChatGPT and it didn't answer it. So this one wouldn't work, but sounds like it would work, you know. Then this thing, the scale up. So the scale up is like basically like certain costs are fixed, like the capital cost per whatever you're making drops when you make a bigger plant. And the other reason is that the surface, like if you have a small reactor and a big reactor, so if you're doing, like when I was a grad student, I did this polymerization of a cationic polymerization. It's like any impurities would kill the thing, you know. And so I did it in these little like 50 ml things because it could blow up or something. You know, so you didn't want to have too much. And then I wanted to make a bunch of the stuff, so I went to this plant in Canada, and then we made it in this like a room-sized reactor. We made a big batch of it, you know. It's kind of crazy, like, and it had to run liquid nitrogen temperatures. And when I did it in the lab, it was like a little beaker of liquid nitrogen. In Canada, they literally just like sprayed liquid nitrogen out into this giant thing, you know. So it's just like a big cloud. It was crazy. It was pretty insane, but that's what they did. So anyway, but it turns out like you got much better stuff from that gigantic reactor, like human-sized reactor from this little one. And it's because if dirt is a problem, like you have so much less surface area than that reactor per reactant, you know. So a little bit of dirt and the small amount of surface to volume that you have just gets consumed right away, and you get like pure product out of it. But in the little one, it's almost all surface, you know. So in this case, it's similar, like the surface here to volume is the heat transfer. Like you're going to have a lot more heat transfer with a smaller one than with a larger one. I think that's kind of an issue here. I think there's a surface to volume issue in it too. Then there's some other reasons for scale up. Anyway, it didn't seem like people had a real strong feeling about it though, given that it's the main point of chemical engineering. Like the main thing, generally some guy did something in a lab and you're gonna make a plant out of it. Like, why are you doing that? Why wouldn't you just get more labs, you know, like make a bunch of little labs that would just crank it out, like do it in China or something, you know. But so anyway, there are reasons. So it didn't, yeah, those two you should be able to answer for any kind of process. Like, why is it better? Why is scaling it up going to be better, you know? Anyway, some people got that perfectly. Like, in other words, two groups out of like 16, 2 or 3. But anyway, and then this thing, I wanted to to get the numbers out of the. All right, the way I calculated this, it didn't have any impact at all, but it was pretty convincing that people did this and they found out that it did have an impact. It was like 50%, 25 to 50% is the heat of condensation compared to the solar irradiation. So at first I thought that was kind of crazy, like it wouldn't possibly have any contribution to it at all compared to the solar irradiance. But it turns out it does, like it's got a huge contribution. So anyway, again, it's those like 2 or 3 groups could figure that out from the numbers that were given there. And everyone else just kind of blew it off or whatever, I guess. But so anyway, that was that. Thought I'd go through that because people weren't doing that great with it. It might be that you're just not motivated to do it, or it could be that you don't know why you do scale up. So this, because you don't know why you do scale up, you should figure it out. If it's just because it's like not that important, it doesn't matter. But it could be like someday you'll be in a meeting or something, like it would be good to know like why you're doing what you're doing, you know? So this business this week could be equally challenging, but if you watch that video, then you can get this dry bulb, wet bulb business. Like that tells you exactly how to do this. I mean, I kind of went through it in class, but basically they do a better job. And then, but it is like a 5-minute video, so it's a time commitment. And then the seawater, you need to use there's a thermo thing about the shift in the boiling point for when you add a salt into water. That you can Google, or you can find it in a thermal book. I think so. These are all just kind of calculations. This could be something that's going down hard too this week, but it's hard to tell. And it's just those 2 papers to glance at, so hopefully that's okay. See how you can do on it then. So I get, so there's this whatever, this recycle place can do a tour, but it's like the last day of classes. I mean, that's not going to work out. December 1st. So far, no one said they would go, I think. So maybe we just drop that. And then the water plant, 2 people want to go so far. So that might be doable. Like if we get 3 more, that would be good. I mean, especially if the 2 people that said they wanted to go could recruit some other people to go, that'd be good. Then what else? There's one other thing, right?
80 acres.
Oh, 80 acres. Yeah, that sounds like it's gonna go. Like you're going. So that's one person. Maybe you can talk some other people into go. If you're driving up there, then you probably are you gonna just go home from there or something? Or?
Yeah.
Oh, all right. Well, there it is.
Drop off on campus.
Oh, you're gonna drive back here? Oh, okay. All right. Oh, then yeah, you can fill your car out.
Like home is 3 minutes.
Oh, okay. All right. I'm thinking, I was just talking to some people in the other class and they're going to Columbus. It's like that wouldn't work out because this would be like on the way kind of to Dayton at least. But anyway, all right. So maybe we can talk some other people into that one. And then the water plant thing, maybe people will do it. I think we get 2, so it's likely, probably I could ask the environmental people, some will want to do it. I'm not sure, there's no environmentals in here, right? It's just straight chemical. Yeah, maybe I should fish over to the environmental, someone will go. Anyway, yeah, that's it. I think that's it. Oh, and then I got Maoping 2's gonna talk, but not until the end of like November 28th or something. Like, I don't know why he said then, but I said it could be like any Tuesday, Thursday, and it's like November 28th, which is also like a couple days before the end of the semester. But anyway, by then we'll definitely have covered some stuff on like bio stuff, like biofuel type thing. He's got a lot to say about it. Like that's all he does is make biofuel. He worked at the Canadian Pulp and Paper Institute or something. Somehow he has like background in paper. And somehow from that, he went to the Department of Energy. I think he was in Oak Ridge, or something, doing this biofuel business. So he's been doing it a while. He's kind of an expert in that area. Do any of you work with him? He takes some students for doing research, but anyway, he's got a lab up in Rhodes, actually, upstairs where they have biofuel stuff. Anyway, so he's pretty pro biofuel. Anyway, so I kind of went through the psychometric chart. That's partly this week is like using that, how to use it. And then, so you can engineer this thing to do, and so there's companies that have engineered like this kind of humidify, cool the air with the cross flow, then humidify it to try to get the temperature drop in the system, you know. So in climates where you aren't in a super dry area, you know. So like this is a Australian company that sells this, where you do go through a heating cycle and a cooling cycle. It's kind of a diagram or something like that. So ambient wet, warm air, and you end up with cold, moist air going into the house. And you do it by first like dehumidifying the air. So these are isothalpic lines. So if you pull the adiabatic line, so if you pull the water off by heating it up, so you evaporate the water, then you go along an adiabatic line, you get to 2. And then if you go from there and evaporate the remaining water from the air, drive over to 3, regeneration, and then you spray water on it and evaporate water from it. That goes adiabatic up here. Oh, this is just cooling. I guess this stage is just cooling. It's like a cross flow between the exiting and entering. So that's just cooling. And then you evaporate to get the coldest temperature that you want to go into 4. It warms up in the house and humidifies a little bit. And then you do another spray to bring it up to 6. So that cools it and it humidifies it. And then in 6 to 7, there's like a heat transfer. So you heat up the air going out and you cool down the air going in. And then heat input would be solar for 8 to 9. Or 7 to 8 is the solar heating. And then 8 to 9 is humidifying the air again. So you dehumidify this air and humidify the exiting air. So you end up with hot, wet air going out, and then cold, moist air going into the house. So that's basically this rig that these people sell, you know. I mean, it's possible to do this kind of engineered system so it's air conditioning with it's just using water and solar heat. There's no compressor in it or anything. There's fans. There's no compression in it. So it's pretty simple. So anyway, that brings you to so as far as like that's evaporative cooling using water. If you use some other chemicals to evaporative cool, then you can do things like make a refrigerator with ammonia. That's kind of like I was looking for that accident, you know, and I found something like, let's see, get back over here in Houston, right? Let's see. It's like a news thing. There's some TV station in Houston, Borden in Houston. Oh, so this thing I saw was like in 2018, but it looked like it was so old. Anyway, you can see there's just in Houston, there's like 3 ammonia plants blowing up. This is the one I saw this morning. I thought everyone looked like they were so old, but I thought, well, maybe it's Texas, you know. It's just how Texas is. But let's see. So they show a site where this ammonia refrigerator blows up. It's usually like startup. It's like when this thing happens. So you get like a rush, ammonia vaporizes, you get a rush, And ammonia is a flammable. You can use it as a fuel. Yes, see, these guys look like they're from the 80s. That's what I was thinking. And then even the cars and everything look like they're from the 80s. I don't know why the audio isn't working. But anyway, that's the kind of thing that happened. They couldn't figure out, oh, it smells like ammonia. It's a Borden, I forget, they're freezing food anyway. They use ammonia refrigeration to freeze food because you can get this rapid cooling when the ammonia evaporates. And this blew out, took out a whole block in Houston. Right? It kind of looks like Houston. It's complete destruction of everything. It's not the only one, but I just saw that. Like this morning, I was looking for the one in the bayous, you know.
I think this is the video.
Yeah,
One of
yeah. So should I just look for CSB?
look up shopping system.
Look up what?
Shopping the system. At the moment.
Oh, there it was. Ammonia refrigeration explosion. Oh yeah. So they made a video of the whole thing. They go through the entire process. Did you look at that? Or, yeah, so they go through actually the entire, this is exactly what I was looking for. Yeah, they did a whole study of like exactly
Collins of anhydrous. August 23rd, 2010. The Millard Refrigerated Services Facility in Theodore, Alabama. More than 32,000 pounds of anhydrous ammonia was released to the atmosphere after a pipe within the plant's refrigeration system catastrophically failed. The Chemical Safety Board investigated and found that the ruptured pipe was caused by hydraulic shock, which is defined as a sudden localized pressure surge in piping or equipment, resulting from a rapid change in the velocity of a flowing liquid. Following its investigation, the CSB released a safety bulletin describing key lessons for preventing hydraulic shock in industrial refrigeration systems, which, if followed, can prevent dangerous accidents like the one at Millard. In 2010, Millard Refrigerated Services operated a frozen poultry export facility near Mobile, Alabama. The facility maintained a 143,000-pound capacity ammonia refrigeration system with 8 separate freezers. Within the system, low-temperature liquid ammonia is pumped through evaporator coils. As the liquid ammonia evaporates, heat is absorbed, cooling the freezers. During the process, the outside of the evaporator coils builds up frost due to contact with moisture in the surrounding air. Unless this frost is removed, it will reduce the ability of the coils to effectively cool the freezers. To avoid this, defrost cycles are initiated periodically. During a defrost,
Kind of a weird movie. It's not weird. It's interesting, but it's like the Crazy Scientist movie. Do you want to hear this whole thing? Or? Okay.
cycle, the low-temperature liquid ammonia is removed from the evaporator coils completely and replaced by hot, high-temperature ammonia gas, which fills the coils and melts the frost on the outside surface. Once the frost is melted, the hot condensed liquid and remaining gas are removed from the evaporator coils before low-temperature liquid ammonia is pumped back in to resume normal operations. On August 22, 2010, the Millard facility experienced a loss of power that lasted more than 7 hours. During that time, the refrigeration system was shut down. The next day, the system regained power and was up and running, though operators reported certain problems. While doing some troubleshooting, an operator cleared alarms in the control system, which reset the refrigeration cycle on a group of freezer evaporators that were in the process of defrosting. The control system reset triggered a valve to open, and low-temperature liquid ammonia was fed back into the evaporator coils before removing the hot ammonia gas. This caused the hot, high-pressure ammonia gas to rapidly condense into a liquid. A vacuum was created where the gas had condensed. The void sent a wave of liquid ammonia through the piping, causing a sudden pressure surge known as hydraulic shock. The pressure surge ruptured the evaporator piping manifold inside one of the freezers and its associated 12-inch piping on the roof of the facility. 32,100 pounds of ammonia were released into the surrounding environment. The large cloud traveled a quarter mile from the facility south toward an area where 800 contractors were working outside on a cleanup site for the Deepwater Horizon oil spill. 153 people were exposed to toxic anhydrous ammonia. 32 of the off-site workers required hospitalization. 4 of them were admitted to an intensive care unit. During its investigation, the CSB learned that the operator who was attempting to troubleshoot equipment issues after the power outage manually cleared alarms that reset the evaporator controls. Due to the reset, the control system did not recognize that the evaporator was already in the process of defrosting and allowed the refrigeration cycle to start without removing the hot ammonia gas from the evaporator coils. The CSB notes that one lesson learned is to avoid the manual interruption of evaporators during defrosting and to ensure that control systems are equipped with security devices so that only trained and authorized personnel may manually override programmed operations. And after an unintended interruption of service, hydraulic shock can be avoided by programming the control system to automatically remove contents from the evaporator coils prior to restarting refrigeration. The CSB also found that the evaporators at the Millard facility were designed so that one set of valves controlled 4 separate evaporator coils. As a result, the contents of all 4 coils connected to that valve group were involved in the hydraulic shock event, leading to a larger, more hazardous pressure surge. The CSB notes that when designing ammonia refrigeration systems, each evaporator coil should be controlled by a separate set of valves. And the CSB found that immediately after discovering the ammonia release, a decision was made to isolate the source of the leak while the refrigeration system was still operating, instead of initiating an emergency shutdown. A final lesson learned from the CSB's investigation is that an emergency shutdown should be activated in the event of an ammonia release if a leak cannot be promptly isolated and controlled. Doing so can greatly reduce the amount of ammonia released during an accident. The CSB believes that if ammonia refrigeration facilities follow the lessons learned from its investigation into the accident at Millard Refrigerated Services, dangerous hydraulic shock events can be avoided. For more information about the CSB's Millard Refrigerated Services investigation, please visit csb.gov.
How to quit it. All right, Mosquito Coast. How do you spell mosquito? Right. Taylor, I guess. Yeah, it's a movie about an ammonia refrigerator. The guy goes to the. He's like. This isn't it. This is some other movie. Oh, maybe it is it. Anyway, he has this idea. He goes to Central America, and there's like tribes, and he shows them like he wants to bring ice to them. Anyway, he builds a giant ammonia refrigerator, and then it blows up. Like the end of all these is like the ammonia refrigerator blows up. Okay, that's going to be the scenario. But let that be a lesson to you. And we made one. That's an ammonia refrigerator. No, it didn't work. It didn't really work. Basically, you have carbon, activated carbon up here, and it can absorb the ammonia, or methanol or ethanol. And then sunlight hits it, the ammonia comes off. Then if you run it through like a shaded area, it can condense into a liquid. And then if you get the pressure right, it'll evaporate. And when ammonia evaporates, it takes a big enthalpy, so it just freezes anything here. It just makes ice. And then it goes up and gets absorbed back by the carbon black if it's nighttime or if it's covered. And then when the sun, so you use the sun as like a compressor. Basically the sunlight releases the ammonia, which makes it pressure. It's like a compressor, and that goes down and condenses. It's kind of a simple setup. The problem is to anhydrous ammonia. That's the first problem. You saw the problems with that. The second problem is that you got to get the pressures exactly right in this thing. You can see it's a pressure cycle. And if you don't have the pressures right, this isn't going to work. Like, it's hard to get the pressures right. Yeah, we made a box like that. So this is a popular item. Like, we didn't invent this idea. So this is Anthony Tong's like thing he made. He welded this all together, and like that's a milk bottle thing. And anyway, it never actually worked right because of the pressures. Like, we couldn't get the pressures right. And we were using, I think we were using methanol in this. So that, like, ethanol is much safer. Methanol makes you go blind, like the vapors from it. You absorb it through your eyes. So it's a pretty highly toxic thing. It's what they try when you get moonshine. Bad moonshine has methanol in it, and it's basically because you absorb it through your eyes when you drink it. It makes you blind. So anyway, ethanol is safer to use, but you can't get as cold. So you can only like chill things down with ethanol. And then methanol, you can freeze things, but it's kind of like dangerous. We're using methanol. And then ammonia is like really kind of dangerous to use in a sense, you know. So we didn't use ammonia. But ammonia is what commercial devices use mostly. This is at University of Dayton. They made an ethanol. They made one of these using ethanol, and they got it to work. Apparently, at least they said they got it to work. And they took it to Central America and cooled something there. Okay, so a lot of people have done this. This is like Saudi Arabia. So basically everyone's played around with this thing. These guys in Dar es Salaam. All right, so ammonia is like better because you get a much bigger bang for your buck with it. You can cool, and the boiling point of ammonia, it's slightly reduced pressure is like well below freezing. It's like -10 or -20 C, you know. So Cincinnati, like 1920 or 30, this guy Crosley was like the Thomas Edison of Cincinnati. He made cars. There were Crosley cars. This Crosley Stadium was the original Red Stadium. So he was kind of like, I don't know, he's a big guy in Cincinnati. Anyway, he also invented this Crosley icy ball, which is like ammonia and water. So ammonia is instead of carbon, you can use water. Water will absorb the ammonia. And if you heat up the ammonia comes off, and then you can condense the ammonia on the other side. Then that part you refrigerate with. Yes. Yes, Crosley Tower. He's like the most famous guy from the Cincinnati in the 1910s. I think he owned also WLW. I think he brought that radio station online, which is also why they had Radio America or whatever it is, Radio Free something, Radio Free Europe. What's it called? Voice of America, like in Loveland. He's part of that too. WLW was the strongest radio station ever. It could reach 80% of the U.S. population, and they produce like shows in Cincinnati and stuff, like radio drama and things. It was like almost like a Los Angeles of the time, you know. Before they had TV, they had silent movies and they had radio. It's like basically Cincinnati was the center of all that, and Crosley was kind of part of the heart of that. But he also invented a bunch of other stuff. He was like Thomas Edison. Right? There's a bunch of Crosley inventions. Anyway, this is one of them. So Crosley actually shipped like 10,000 of these to like Tanzania, to East Africa, with the idea that they could have refrigeration, because all you need is a fire to heat up this side, or you can use sunlight. Like you can use a solar concentrator to get sunlight on this and do the same thing and refrigerate with sunlight with it. So anyway, that's kind of his thing. There's a video of this online where someone's found one of these and gotten it to run. I mean, it's a high pressure operation. I don't have the pressure scale here, but basically there's a risk in something that's over 100 years old, you know, then if you put high pressure on it and it's ammonia, you already saw what ammonia can do. So, but it is, so it's pretty simple. It's just water absorbs the ammonia, then you boil it, the ammonia comes off, the ammonia evaporates back into the water, then you can cool with it. You don't have any compressor. So the water is a compressor. right? And you use heat to make cold. So it's basically trash heat can be used to refrigerate. It's a good idea. The problem is it's clunky, right? I mean, it's this thing you have to manually use the handle, and then this thing, like there's a lot of pipes, like convincing someone that so in the developing world, there's people in the country that need this kind of thing, and people in the city that have like electric refrigerator. And the people in there are cousins or brother and sister or something. So they see how the other half lives, you know. If you say like, oh, look at this great thing, we can refrigerate and you can get ice, it's gonna be amazing. They're like, then they see their cousin in the city and they have like a regular refrigerator, you know, and it's like, no, it's not gonna exactly work. Nobody wants this thing. That's the problem with the whole rig. This is a classic example of like, to an engineer, this is a great idea. To a marketing person, this is just worthless. So it's a pretty good example of that type thing. But same with Crosley, like he was kind of a technical person, right? So if you go to the museum center, they have Crosley cars in there. Like he made a car. I don't know. Anyway, so these people in Maryland, these are ammonia refrigerators, and they're using it to cool milk, and apparently it saves a lot. Like the milk was going bad. So what they do is they have a cooperative where people put the milk together and like deposit the milk into refrigeration units, and then they take it out to sell it. So it's kind of more like a cooperative system, and they have this refrigeration unit to go with it, because each individual farmer wouldn't have this kind of setup. You can see they're just using solar concentrators to get the heat to evaporate the ammonia water thing and get ammonia, and then ammonia cools and they make ice for it. That's basically the idea. They make these blocks of ice and they put the blocks of ice and they put the milk in it. Apparently it was effective. You see, this is the cooperative, this something very cooperative. I think this is in like Kenya or someplace in East Africa. Not sure if it says here. Kowal district. It's in Kenya. Anyway, so oh yeah, Isaac, whatever. That's just showing them operating the thing. So this thing involves the way it's set up, like so during the day it heats and boils the ammonia water, and then at night, so it isn't a constant refrigeration in it. So it makes ice, and then you need to use then the ice is storing the energy, which makes you think like, so this idea of making ice is a whole kind of segment of this alternative cooling thing. Like people just, right, so for instance, power is really cheap at night and expensive during the day because everyone's running air conditioners during the day in certain parts of the country. So the idea is like, well, when the electricity is cheap, then at night, then you can just make a ton of ice and just use that, have that somehow conveyed into refrigeration so you can air condition places with it and humidify too if you want. But so basically this idea is this kind of stage-wise ice making, similar to this machine, you know. There's some places that are, there's some like demo projects where they're doing that to cool down, like tourist centers and things like that, you know, in California. So it's an energy free, or it's just using solar energy to run the whole thing. There's no other energy in it. So basically there's a pump, but it isn't much. Basically it's just solar energy. And then you can make, you know, you can do refrigeration or air conditioning with it if you want. The problem again is like this is pretty clunky. Like you're taking this to East Africa, like look at what the thing is, and if it, so it's the potential you're going to leak out ammonia. You could see what the potential is from the frozen food factory, you know. So you could get just the same kind of thermal shock in this system. And then what would happen, like this guy's going to be blind or something, right? So I mean, it's kind of a dangerous setup in a sense. It makes a lot of sense one hand, on the other hand, it's not, it's kind of nutty. This is in Tanzania, so they're doing the same thing. So everybody's doing this. Like they have a solar concentrator, they have, you know, refrigerated part to the thing. Anyway, it's the same idea. Didn't get to work either. I mean, so then this is industrial. So if you have a salt water, so water will selectively go to salt water, and you can use heat to separate the water vapor from a salt brine solution. Right, and that's another way to do evaporative with lithium. And that's an industrial scale cooling also like the ammonia. But these are industrial scale absorption refrigerators that use heat to produce cooling. Right, the generated part is using heat and then kind of running the water vapor through this system. There's kind of designs for that, but so they're it's more efficient than this. So this ammonia refrigerator is what like if you have an RV refrigerator and it's a propane refrigerator, they use ammonia. It's basically an ammonia refrigerator, and the propane does the heating instead of the sunlight. If you've ever seen a propane refrigerator. This is a picture of the back of a propane refrigerator. It's got ammonia gas, blah blah blah, water, and then it's got somewhere it's got propane heating up, but separating it, boils it. And then there's this is someplace in Tunisia where they're using solar to heat up the ammonia to do cooling. Again, it's kind of like a demo project. It isn't, except for RVs, where you use gas to heat it. There isn't. Even though ammonia refrigerators and this kind of evaporative refrigerators have been around since probably the 1950s or something. Well, no, because the Crosley icy ball was like 1920. So it's been around a long time and it hasn't really caught on, except in RVs where you use propane to heat it, not sunlight or some other like waste heat. So other than demo projects, the ammonia refrigerator hasn't really, there's been a lot of interest in it and it hasn't really gone anywhere. That's the bottom line. And Einstein, so Einstein has one patent, and it's an ammonia refrigerator, right? Some kind of complicated butane ammonia, whatever refrigerator, basically. It's kind of funny. They call it the Einstein refrigerator. I think he signed, so I think his signature is down here somewhere. Albert Einstein, the top signature, like invented this. He worked, Einstein worked at the patent office in Switzerland, in Bern, Switzerland. I went to his, you can tour his apartment where he lived. So I went there once, but it's kind of interesting. That's where he did a lot of the theoretical work he did. So he wrote the papers in that apartment. So it's kind of interesting to see it, but it's not really worth going out of the way to see it. But if you're in Bern, it's one of the things you can see. Anyway, so he did invent a refrigerator. This is like, there's a link to this book on the webpage. It's like Solar Energy for the Evil Genius or something. And they tell you how to build an ammonia refrigerator. They don't tell you where you're going to get anhydrous ammonia from. So they just say, go buy 1.5 pounds of ammonia. When we were building that thing, we looked to see where can you buy 1.5 pounds of anhydrous ammonia. It's like no one sells that. Like they sell it in water, but like a 2% solution in water, but you can't get. You could condense it from that, but you'd have to go through a lot of cleaning products to get the ammonia that you need for the sun. So then this guy, just to show you that this is exactly the same thing as a Crosley ball, but this guy did a TED talk on it, how he's going to save the world with this, basically the Crosley ball from 1920. It's kind of like the same thing, the two balls are connected into one unit. That's the difference. And he goes on and on about how he used Caltech and Berkeley, all the scientists put their input into designing this device, and he took it somewhere to Saudi Arabia or something where they could take it out into the desert and make ice to keep the vaccine safe. And it's pretty funny how people, anyway, this is what kind of thing, if you're doing that, probably I don't know if I'll give you that homework, but there's a homework where it's okay, build this thing, figure out how much money it is for the pipe and the anhydrous ammonia, wherever you're going to get it. And then compare it to the price of buy this refrigerator and then just buy a solar panel, right? And then this is exactly what people want, They don't want this kind of piping system that you hack together. They want something it's a refrigerator. You can tell it's a refrigerator. or even a vaccine refrigerator, at least it's like a freezer or something, right? So anyway, whenever you see like, if you Google like solar power refrigerator, this is what you're gonna find, is like a solar panel and a refrigerator. You know, so it's kind of funny, like the competition, what people want, you know, it's like, the idea is like pretty good, but it's hard to tell like where that's gonna go. So that was one homework. I'm not sure I'll do that this year, but you may see that again. Then, so then there's just a bunch of things, different things in here, like the idea of just like use solar heating, like this kind of barn thing. Then I was in Kentucky the other day, like down by the booze area, whatever, bourbon. It's like, wow, the buildings are all black, so they must be doing the same thing. Because if you go in they don't really grow tobacco anymore, as far as I know. But when I was growing up, like in New England, they grew the outside layers of cigar tobacco, which is some special tobacco that grows in a cold climate. And they had this kind of barn like all over the place in Connecticut. And then in Kentucky, like in the 1990s or something, these barns were all over the place to dry the tobacco leaves, you know, it's just solar heating. So then I went down there to the bourbon thing and they're all black. The buildings are all black. I thought, okay, they must heat up the bourbon things with this, right? But it isn't. When bourbon, the alcohol comes out, the ethanol, and like there's a certain kind of fungus, a black fungus that loves ethanol, apparently. So it's like every building, and in fact, if you look, like even the street signs and everything is black there. So it's not just the bourbon warehouses that are black. So it isn't, they're not trying to get heat with it. Anyway, so in this case, they are trying to like dry out the stuff using solar heat, right? So people have kind of designed that idea, like put a plastic sheet, have black on the inside, then you can dry whatever it is you want to dry.
Did you go to like a distillery?
I didn't, I drove by it.
There's actually a reason bourbon works so well in Kentucky and it's aged in Kentucky because of the seasons. So it ages better because it gets warm in the summertime and then comes back in on itself in the winter time.
All right.
So like the buildings that they use to age it and everything,
Yeah.
it's kind of a little scientific.
But the black isn't though, right?
No, they use brick buildings. They're called brick houses.
Yeah, but they have the ones I saw, like they're black, you know, they're colored. I mean, in other words, so then I looked it up. I thought, okay, it's got to be the same thing. Like, and I thought this is a pretty good example. I'll show you this. But basically, it's not at all. It's just like this fungus grows there. And then if you Google the fungus, you'll see like the street signs, everything is black. It's not just the barns, you know. And apparently, like the ethanol, some of it evaporates. But it's pretty weird. Yeah, I don't know anything about bourbon, but I didn't go there to see the bourbon. I went down to there's a monk place down there somewhere. I forget the name of it. Gethsemane or something. And it's this guy who wrote these books in the 1960s and 70s. Anyway, it's kind of interesting place, but it's definitely not worth going to. But it's interesting. It's like famous, you know.
Yeah.
Like it was like Martin Luther King and this guy and this one other guy. They were doing stuff, you know, they were writing books and things about how to change the world type thing. So it's kind of like a point. I thought someone mentioned it to me, so I went down there, and it's right in the middle of bourbon country. They even have like, I forget what they have. They have something like the monks make something like cheese or something, and there's like bourbon cheese that these monks make there. Anyway, it's kind of weird. Definitely not worth going to though.
Been there, they make fudge.
Oh, fudge, that's it, bourbon fudge, yeah, okay. Did you think it was worth going to that place? I mean, to me, it was like, I had pretty high expectations because the guy's pretty famous. I forget his name. What's the guy's name? Anyway,
Years.
he's pretty famous. He wrote a lot of books, but you go there and there's like nothing there. It's just like totally nothing. And the part that you'd want to see is like the Hermitage, whatever, where he wrote his books. You can't go there. It's like off limits, you know.
Is it still like a working monastery? There's still
Yeah. Yeah, I mean, I don't know, if you're interested in that, it's probably worth it, I guess. Or if you did like people do retreats there, it might be worth doing that, like kind of go out in the monk land. And
Yeah, that's what I ended up doing. Like the monks there do like a vow of silence and then retreats you like this.
yeah, I mean, that's a good thing, but just going to see it isn't worth it. But that would be like an experience that could change your life, you know, but basically visiting it and seeing the bourbon cheese or whatever, fudge, you know. I don't know. It was all right. It's pretty out there. Anyway, I saw these bourbon barns and it reminded me of that thing, but it isn't the same thing at all. But they did paint these black to try to dry the stuff. And anyway, so people studied this. Like this is Virginia Tech. They're making these studies on how to make a dryer, a solar dryer. And then there's a study was done in Ethiopia on this stuff somewhere. It's in here someplace, but I guess I don't know where it is. But anyway, that's kind of like solar heating, you know, like to dry textiles and stuff, or no, there's one, I think I showed it before, to dry skins, and then they're also drying like herbs and things. You know, so like people study that for solar versus using diesel fuel to dry stuff. And it makes sense, kind of like easy to do. Anyway, so we were looking at, so if you, in Africa, like everyone burns charcoal, and because this is like like in Ethiopia, they invented coffee, like donkeys and coffee are from Ethiopia. A couple other things, like humanity kind of came from there too. But anyway, so they do this coffee ceremony where you have charcoal and you heat the water up in this thing, and it's like they have popcorn with it. It's kind of a whole like ceremony that people do. Like when they like you, they do this for you. They make you this coffee, Ethiopian coffee thing. But it has to be done with charcoal. You can't do it with like electric heater or a gas heater or something, right? So if you drive around, there's all these charcoal that people make. So they basically dig a pit. They take sticks. So there's no trees because they deforested everything. Like the country was once 80% forest, and now except for the parks and things, there's no forest at all. So I think it's like 2 or 3% forest now. And basically anything that grows, they'll make into charcoal like this, which is bad because it's bad because they chop down the trees, but it's also like the energy of that wood that they chop down. I think 70% of it is thrown away when you make charcoal, but it makes something that burns better and you can do the coffee ceremony with. So everybody wants that. So if you go out in the country, so in the city, these things are expensive. In the country, they sell them at the side of the road. But if you bring it back into the city, some guy with an AK-47 will say like, "What's on your roof?" Like you'll need to pay him off, like to be able to take it into the city because it's illegal to bring because of the deforestation thing, right? So the charcoal, all the governments in Africa trying to get rid of charcoal, like they just want to stop people from doing this, but not having a good time doing that. Anyway, so there's something to be said about doing something about charcoal. So I don't know, a while back I had a high school student doing this, and he did stuff with that Go Sun people, you know, to try to do this. So basically you can take wood and you can put it into this one of these evacuated tubes, and then have a parabolic reflector and get the sunlight on it. And then instead of digging a pit, so what they do is they'll dig a pit and then throw all the wood into the pit, light it on fire, and then pour dirt onto the top of it and let it kind of smolder and eventually get charcoal. And then dig it up, and then like, you know, after a couple days, dig it up and then wrap it up into these things and sell it. So these things were all made in a pit somewhere. So several ways to make it better than that. You can use a retort oven, which is a little bit slightly higher tech than the pit. Ends up with kind of the same thing. And then the new way to do it would be to kind of use a solar concentrator where you don't waste any of the energy of it. So basically when you use a solar concentrator, you get wood gas from this, which is like you can burn it. You also get tar and you get water. So the tar and water are a problem. The wood gas can burn. So in a retort oven, there's a video of a retort oven here somewhere. This thing, but I'm not sure how this is going to work. Oops. These never work, right? If I do that, I say yes. Oh wait, is this actually on YouTube? No. No, this is just my thing. I think it came back and said like I won't do it. If I click this copy link, that's good. It's good sign. Let me just do this. So they show what a retort oven is. It's not as good as the Mosquito Coast trailer, which is still has running. Control paste. All right, let me try to get it here. Oh, I don't know why I can't get this to work, man. All right, select all. Copy link. Did that really copy the link? Paste. No, it doesn't have it. Didn't really copy it. Or it copied it and didn't. You have to do this. Did that work? No, it's the same thing. Let's figure out like, how to make this thing work right. On my computer, no problem. This is kind of worth seeing. I mean, it's debatable, but we got 5 minutes, so it won't take more than 5 minutes. And it is fire. It's in some guy's backyard, who knows where. So he's got this is called a retort oven. So the idea is like you stuff the wood into the middle, right? And the wood is going to make the charcoal you stuff in the middle. And then the off gas comes off. So if you build a fire under it, and then that heats up the wood, then the wood starts, first it comes off with steam that doesn't burn. And then it comes off with like tar mixed with wood gas, which is like vaporized phenol, whatever junk is in there. And then that you can retort, you can like make it come back in underneath. So you can use that to heat, so it heats itself. So the energy that you would use to run a fire to make charcoal, you get out of the wood itself. So it's more efficient, slightly more efficient than a so anyway, the fire part, so he starts the fire. So he's got the fire started. So this is just the starter fire in the bottom, and the outside of this. So he's got a tube that shoots out the gases coming off the wood, which is from the middle, I think. And then the gases off the wood is coming back in and can catch on fire again. So he's also got a vent at the top where you can see like exactly what's going on. Like, is it steam or is it something flammable? That's showing this off gas stuff coming from the wood gas basically. Could be inside there is the fire that he's making the charcoal with. Then finally, there's a big flame at some point here. Once that stuff stops being water vapor and starts being the stuff you want to burn, then there's kind of an explosion. Yes. And then the thing would just torch. And the wood, so the wood isn't burning, the wood's in an enclosed area, and there's a fire that's just heating the wood. So you're just kind of cooking the wood inside this retort oven. That's the idea. So there's a setup for this in Tanzania and Dar es Salaam on the coast, and at the university, where they're trying to use instead of chopping down the wood, use the sewage sludge. So they have retort ovens like this, and they take sewage sludge and put it into pellets, and then cook it to make charcoal with it. And then the idea is like to sell that to people to use to make coffee or whatever. They don't make coffee like that in Tanzania, but to cook food. So that's the charcoal. They let it cool for like 2 days, and then like that stuff is left in there. So that's how you make charcoal. That's kind of basically in a retort oven. So let me show you the Dar es Salaam guys. That's their setup for doing that. They make these little briquettes. The question is like, we buy this kind of pillow shaped briquette, they call it, and they make these cylindrical briquettes. They make a bunch of different shaped briquettes. The thing is like the Ethiopian guys don't really want briquettes, they want exactly what they want is what they have, this kind of stick thing. And if I have that, this is what they want. Sticks of charcoal that they can do this with, like set it up like that. And it's the smell of it and things too, so maybe the sewage stuff won't exactly work. It's got, like the smoke goes into the food, right? So they don't want electric cooking. They want this kind of, anyway, so it's about out of time, I guess. But like if you take one of those charcoals, people have figured out, guys from Mexico figured out like what fraction is like people that make it are getting like 20%. Guys that dig the pit, make the charcoal. Then the rest of it goes to like whatever, all of the things. Like most of the money isn't theirs. Like it says like somewhere here, police bribes 20 to 30%. It's like basically that's probably underestimated. It's like you try to, if you include like, so when they sell it at the side of the road in the country, they've already paid 20%. When you get to the city, it's like double the price. So you have to shell out to some guy with a gun, like just give him the money. He'll let you take the charcoal into the city. Once you get it in the city, it's probably worth 4 times that. You know, so if you want to sell it, mostly people give it to their friends or something. Anyway, why don't we quit there and kind of, so I have a bunch of stuff. I have some stuff on wind I'll do probably, and then there's stuff on photocatalysis, things like that. So anyway, that's about where we're going here. You too.